So welcome to the final lesson on differentiation in year 2 and in the course. And in this lesson, we're going to apply the skills that we've been learning, particularly the chain rule, to some realistic situations involving rates of change. And we're going to construct some simple differential equations as well. And these differential equations you'll be able to solve once we move on to the integration chapter. You'll find out as well, depending on which fields you go into and future projects that you might be doing, that differential equations are absolutely fundamental, and you'll certainly be coming across them again. Okay, so that's the introduction. Could you please pause the video and try the 4 warm-up questions? Okay, and let's have a look at the solutions. Okay, so for question 1, you'll probably think this is a bit different to what we normally do. We have a balloon, and the length of the balloon is x. It has a surface area of A and a volume V. Now, the balloon is inflated such that x, A, and V all increase over a time t, and you'll be familiar with this from experience, I would have thought. So the first question in this first sub-question is, circle the derivative that represents the rate of change. That's in italics. The rate of change, that's what calculus does. It tells us the rates of change of the volume of the balloon with respect to time. Okay, so we've got some variables in here. We know that V is the volume, X is the length, the surface area is A, and time is T. So with respect to time implies that I need to have the time variable in the denominator, because normally when we differentiate y with respect to x, don't we? So if I'm differentiating the volume with respect to time here, that's telling me I need to have a derivative which features v in the numerator and t in the denominator. Okay, dv by dt, in other words. So can we see dv by dt? Okay, there it is. Okay, so that's the rate of change of the volume with respect to time. Okay, and for part B, we're talking about compound units. So combinations of measurements for different things. So which compound units could be used to represent the rate of change of surface area? Okay, surface areas come up first. Let's just highlight that with respect to time. Okay, so once again, time is what's been differentiated with respect to, so that's going to be on the bottom of the derivative. Now, if that's the case, then we need some time units. Now, which of these are time units? Well, if we go through each derivative one by one, we can see in the first one we've got centimeters squared, which is, of course, that's a unit of area. Okay, so is millimeters squared. Now, let's just focus on those two for a second. This is an area, and this is an area. Now, what is the other part? Well, this is S is seconds. That's the standard international units for time. So that's an area with respect to a time. Okay, and so is this. So that's an area with respect to a time. So it looks like we've got 2 candidates there. So millimeters squared per square second. However, if you notice, the first one, it has s to the power -1. So we're going to have t to the power 1 there. This is t squared. Okay, so that's the derivative of the area with respect to the square of the time. Okay, that's not what we want. Now, if we look further on, we've got s, which is a time variable with respect to an area variable, because we've got an area unit, sorry, time unit with respect to an area unit here. Okay, so that's not what we want either. That seems to be the wrong way around. Okay, let's check the last one. Well, we've got meters cubed there. That's what M stands for. And we've got per second. Now, meters cubed, of course, is a volume. Okay, and that's over a time. So which our surface area with respect to time? Well, it's actually only the first one. Only the first one, because it's the only one with seconds to the power -1, or centimeters squared per second. Okay, so that's the answer. Now, moving on to question 2, we have to find some derivatives. Now, it says a circle has a radius r. Right. Let's have a look closely at this. What do we have to find? Well, we have to find dA by dr. Well, A, which, as we've just established, is area. We're going to use the letter A to represent area. I'm going to need to know what the formula for the area of a circle is. So I'm just going to jot that down. So A equals pi r squared. Okay. Now I need to differentiate A with respect to r. So A is my dependent variable there. My independent variable is r, and pi is a constant. So I can just differentiate this as I would do a normal polynomial like y with respect to x, but this time it's A with respect to r. So if I do that, okay, we've got r to the power 2, so that would be like your x squared. So the 2 is going to come down to the front, and we've got 2 pi, and then we take 1 off the power. Now, notice something quite interesting there, which we're going to explore later. We've actually got 2 pi r as dA by dr, which is actually equal to the circumference of the circle. Now, that's an interesting result, isn't it? So the rate of change of the area with respect to the radius is equal to the circumference. We'll explore that in a moment. And then if we differentiate again, obviously the 2 pi is the coefficient. We're going to keep that. And then we lose the power of r, so we're just going to get 2 pi. Okay, so I hope that makes sense. Okay, now for number 3, we've got some chain rule products here. So this is basically establishing the correct derivatives to create the derivative that we have on the left-hand side. So you'll notice immediately in part A, we have dA by dt. And now I've got the A set up already. That's been given to me. Now, I need to have a dt on the bottom. I'm forced to do that because the left-hand side tells me that's what I have to have. Okay, so I've got to have a dt on the bottom. So I'm going to put that in first. Okay. In order to create that, I've got to cancel the dr, which we can see right here. I've got to cancel that out. The only way I can cancel that out is by putting a dr in the numerator. So my chain product, as I've decided to call it, is dA by dr multiplied by dr by dt. Okay, so I hope that makes sense. Now in the second one, if you didn't get that, by the way, first time round, have a go now. Pause the video and try it again and see if you can do it this time. Now this time we've got dv in the numerator. Now at the moment I've got dA by dx. Now I've got to have a dv somewhere. Now how am I going to do that? Let's try it. So I've got to have dv on top. Now, thinking about this, what is it I want to have on the bottom? I need to have a dx. What I don't want is the dA. I've got to cancel out the dA, so that's going to go on the bottom there. Okay, so that's how I've created the dv by dx. So I can cancel out the dAs and keep the dv and the dx. Now, you can do this more than once, as you can see in part C. So in part C, I've got, again, dv on the top there. Now, so I need to keep that. So I've got dv there already. That's good. What I need in the denominator is dt. Okay, now do I have dt? Well, yeah, I've got the dt there. I've got the dt over here. So that's good. I need to keep those. So what I need to cancel out are these extra variables. I need to cancel out the dA and I need to cancel out the dx. Well, to cancel out the dA in the denominator, I have to have a dA in the numerator. Okay, that's the only way I can cancel that out. And to cancel out the dx in the numerator, I have to have a dx in the denominator. And you can see now, hopefully, that we have the cancellation diagonally here, and I'm left with the dv by dt. So they're little puzzles, essentially, when you're setting up these chain rule products. Okay. Now we're going to move on to question 4, where we have quite a lot of text to sort of plow through. Let's have a go at this. So in number 4, it says, consider the statement. The rate of change of the surface area of a sphere with respect to its radius is directly proportional to its surface area. And it says we can write this as a differential, or as the differential equation, dA by dr equals Ka. So just let's summarize what this has told us. The surface area of a sphere with respect to its radius. So we can replace these with letters, can't we? We've got surface area again here. Now you can tell by the way the differential equation has been written that the surface area must correspond to A and the radius must correspond to R. And the rate of change of the surface area of a sphere with respect to its radius, that whole first, not sentence, but part of a sentence, all that corresponds to the dA by dr, okay, which we've got here. Okay, now it says it's directly proportional to the surface area. Well, directly proportional, you'll be used to using the fish symbol, okay? So it's directly proportional to the surface area. So you could put fish A. In other words, dA by dr is directly proportional to the area, okay? And then the next step would just be to put in a constant, okay, and then set them equal, which is what we've got. So now that we know that, we've got the challenge of writing another differential equation. So it says here, write the following statement as a differential equation. So the rate of change of the volume, okay, let's think about it, the volume of a sphere. So let's call that V. I think that's a sensible thing to do, what we've been doing so far. Okay, with respect to time, okay, with respect to time, so the second variable that I'm interested in is time. With respect to time, so we're going to call that t, little t. Okay, and this is directly proportional. So I know that's my fish symbol. And then the last thing we've got is the radius, okay, which we've been calling r, haven't we? So this is what we will call r. Oops. So let's write that as a differential equation. So the derivative part is the rate of change of the volume with respect to time. So that's my dV by dt. Okay, so that's the first part of the sentence. Is directly proportional to, so I'm going to put the proportional symbol there, the radius r. And there we've got not a differential equation yet, but we've got the mathematical symbols established. Now we can write this as a differential equation. So i.e. dV by dt must be equal to some constant multiplied by the radius. And then we would just have to say where k is a constant. So that's how we break down the text, okay? We're given these statements, we've got to represent them mathematically, and then we can use calculus to deduce numerous things. So that's what we're going to do in this lesson. Okay, now before we actually start looking at rates of change in a bit more detail, I just want to address what came up in the warm-up question 2, when we saw that the rate of change of the area of a circle with respect to its radius is equal to the circumference. And I thought that was an interesting result. I'm just going to explore that a little bit. Now, the first way we saw that was just by differentiating the area. So using the the rule of differentiation that we met last year. Pi r squared is the area, and if we differentiate with respect to r, so dA by dr, just using standard rules, the 2 comes down, we take 1 off the power, so that's 2 pi r, okay, which of course is equal to the circumference, which was what we established. Let's do that again. Now, method 2. Now, if you look at the diagram here, we can actually see how the circle, by increasing its radius by a small amount, we create a new additional area, like an extra layer. Okay, and if we can sort of consider this visually, what's going on, by increasing the radius by a small amount, and I'm just going to label this. Let's say we increase the radius. I've just got a small pink amount there. Let's call that distance dr. Okay, so so this is going to be dr, that width, and we've now got an additional amount of area. And one way we could actually calculate this additional area is in the following way. So if we had, for example, the area of the circle represented by A, like that, and then the area of the shaded region, which we will call dA. So this would have an area of dA. So it's D usually use the letter, or the letter delta for this. It just denotes a small amount, like a small area or a small length or something like that, just a small increase in something. And we can actually figure out what this dA actually is. And it'll look familiar to you, because if we consider the rate of change, this dA part, what is that area? Well, the dA would simply be the area of the outer circle, because this is essentially an annulus, isn't it? So the area of the larger circle, subtract the area of the smaller circle. Now, the area of the larger circle has what area? Well, sorry, I beg your pardon, what radius? Well, if I just add these bits together, we can see that's going to be r plus dr. Okay, that's the area of the large circle. So the area, that's the radius of the large circle. I hope I said that. So that means that the area of the large circle will be pi r plus dr squared. Okay. And then we would have to subtract the area of the circle itself. Okay, pi r squared. Now, if we do that as an exercise, okay, just multiply it all out. So it's going to be pi, and then if we expand this, we're going to have r squared plus 2r dr plus dr all squared, close the bracket, and then subtract pi r squared. All right, now if we do that, we're going to get pi r squared plus 2 pi r dr plus pi dr squared subtract pi r squared. Notice this is very, very reminiscent. In fact, it is differentiation from first principles. Okay, it's the same process. Notice that the pi r squareds are now going to cancel here and here. That's why you lose that power of r when you differentiate, or that power of x. Okay, so what is the dA equal to? So this is simply going to be 2 pi r dr plus pi dr all squared. Okay, now what we're going to do next is we're going to, if we divide everything by dr and take the limit as dr approaches 0, that's what we've not done. So I'm just going to use a bit of, I'm going to cheat and take a bit of space up here. We can see that dA by dr is going to be the limit as the dr approaches 0, but I've divided by dr, so that's going to be just 2 pi r plus dr. Okay, if I divide both sides by dr. And that, of course, is going to give me 2 pi r. Now, if you look that up in a textbook, I've taken a few liberties here with the notation. I technically should have used a delta instead of a d, but it's just to give you the idea that you can do this from first principles as well. And you can see it diagrammatically from first principles. Now, perhaps a more intuitive way is, rather than calculating the area of the annulus like that, what we can do is, for method 3, we can actually say, okay, well, we decided in the second step that this has a width of dr, and as you know from experience, when you do surface area of a cylinder, that when you unravel a layer from a circle, the length of it must be 2 pi r. It must equal the circumference. Okay. Now, it's not quite like that because, as you saw in method 2, there's a little bit extra that has to be argued away, has to tend to 0. But just for simplicity, we'll say, okay, this length must be 2 pi r. Okay. So from one side to the other. Okay. Now, if we call again that area dA, so this is just going to be dA here, we can see that the dA is simply equal to 2 pi r multiplied by the dr. Okay, and then all we have to do is divide both sides by dr. Now, that's sort of shown it mathematically, so using differentiation, first principles, and just with a visual aid. But what you'll notice is it doesn't really explain the rate of change. Why is that rate of change increasing as would the circumference? Well, what's happening is as you increase the radius, obviously the volume, well, this is a 2D shape, but the area is going to increase. And it's going to increase as if you were adding an extra layer of paint or something around the edge. So I'm going to add another layer, and then you add yet another layer around that. Okay, and then so on and so on. You keep going and going, and the circle grows and grows and grows. And that's why it's the circumference, because it's the circumference that is growing essentially. Okay. Right. Okay, moving on to the rates of change. It says here you can use the chain rule to connect rates of change in situations involving more than 2 variables. And we're going to have a look at some examples on how to do that now. Okay, so for our first situation, we've got at time t seconds, so time is probably going to be a variable in this. The radius of a sphere is r centimeters. Its volume is v centimeters cubed, and its surface area is S. The sphere is increasing uniformly at a constant rate of 4 cubic centimeters per second. Now, if you want to, we could just draw what we know, okay? It's a good idea to build like a little summary of everything you know that's given to you in the question, and then we can use each bit of information in parts A and B. So in this situation, we've got this sphere. That's drawn not particularly well by me. It's got a radius of r, like that. Okay, and we'll worry about the time in a moment, but we know the volume V, it's all in centimeters, of course, so V is in centimeters cubed and S is in centimeters squared. So we go to our front sheet of the lesson, and I've given you all the information you need for this. So the volume is 4/3 pi r cubed for a sphere. Okay, the surface area is 4 pi r squared. Okay, so that's using the first sentence. And then we're told that the sphere is increasing uniformly. Now, this is the key step. This is the bit that is not standard information. That is part of the question. So it's increasing uniformly at this rate. Now, we can deduce what the derivative is by the units. So let's look carefully at this. We've got centimeters cubed, okay? So what is that a unit of? Centimeters cubed. Well, of course, that's going to be a volume, okay? And then we have s to the minus 1. So that is clearly a unit of time. So what that is telling us is we've got V over T as the unit. If we do a bit of what used to be called dimensional analysis, we've got a unit of volume over a unit of time, okay? Centimeters cubed per second, or s to the minus 1. Now that tells us what our derivative is going to be. So if the sphere is increasing uniformly at a constant rate of 4 centimeters cubed per second, we can write this down as the following. So it's going to be dv by dt. Okay, and that is simply going to equal 4. Okay, and that is taken from this information right here that I've just deduced. So that's where that came from. Okay, so I've used everything in those first 2 sentences now, and I've created a little summary of all the information. Right, we're now ready to answer part A. So it says, find the rate of increase of the sphere with respect to time. Increase of the radius, sorry, the radius of the sphere. So the radius, which we denote as r, like that, with respect to time, which we have already said is going to be t. Okay, when the radius is 1. Well, we'll worry about that in a minute. So what is part A telling us? Let's write that down mathematically. So it's the rate of increase of the radius with respect to time. So that's dr by dt when r is equal to 1. All right. And again, all that information, this part here, I've deduced from all of this. Okay, I hope that makes sense. Right, so that's the first thing. Let's go ahead and do this. So we need to find dr by dt. This is where we're going to use our chain rule products. So we're going to start with dr by dt. That's the thing we want. Okay, so what I'd really like, I need to have something with a dr on top. Now, this is where we look at our summary. Do I have anything with dr on top? Well, all I've got so far is I've got dv by dt here. So I don't seem to have enough information yet. But what I haven't done is I haven't differentiated anything. So I've got the power of differentiation to play with. So if I know that v is equal to 4/3 pi r cubed, I can write down dv by dr, no problem. So dv by dr is going to be 4/3, no, sorry. It's going to be 4 pi r squared. And notice that's equal to the surface area. This is analogous to the circle situation we were just looking at. Another thing I can do is I can differentiate the surface area. So I can find ds by dr as well. Okay, so that's going to equal 2 times 4, which is 8 pi r, and then take 1 off the power. So I've just added 2 more pieces of information to my summary. Okay. What do I need to do next? Well, there is a clue. This piece of information here, which I've already asterisked, is vital. We really, really need to use that. Otherwise, we're going to be stuck. Okay. And that's why they've given you that information in the first place. So I know I'm going to be using dv by dt. And I also know that I need to have a dt in the denominator over here. I've got to have a dt in the denominator. So let's put the dv by dt in there. Now that's good because that gives me the dr in the numerator and the dt in the denominator. What this forces me to have in the first derivative is dv. I've got to have the dv there because I need to create a cancellation and get the dr by dt that I want. But the good news is I know what dr by dv is because it's simply going to be the reciprocal of this. Okay, so let's put it all together. So this is going to equal 1 over dv by dr multiplied by dv by dt, which we know is just 4. Okay, so this is going to be 1 over 4 pi r squared multiplied by 4. The 4's will cancel. So that's gone and that's gone. So we're left with 1 over pi r squared. And we've now got dr by dt in terms of r, which isn't bad. Okay, we don't have to have it in terms of t. That's not what we're asked to do. So there we have it. So I'll just write that. So therefore, dr by dt, using our summary and all the information we've been given, and just building the derivative that we want from the information we've got, is going to be 1 over pi r squared. So it's, in other words, it's inversely proportional to the area, isn't it? Okay. Now we have to find this derivative when r equals 1. So when r equals 1, simply sub the number in. dr by dt is simply going to equal 1 over, now if you sub 1 in, of course, that's just going to be 1 over pi. Okay, and I'll better put that in a box so we don't get confused. There we go. All right, now I've got the exact answer there. It asks for the answer to 3 significant figures. Okay, so if that's the case, if you're asked to do it like that, what you're going to need to do is, of course, just stick all this in your calculator. Let's get the calculator out. So we do 1 divided by pi, and that's going to be 0.318. And we'll put the units on as well. So this is centimeters per second to 3 significant figures. Okay, so that's part A. Now for part B, it says find the rate at which the surface area is increasing when the radius is 16 centimeters. Okay, now for part B, I'm just going to create a bit of space over on the left-hand side. I'm just going to erase the diagram. I think we've established what we're talking about here. We know it's a circle. So for part B, let's do it over on the left-hand side. Now, we need to set up the derivative. Now, it says the rate at which the surface area is increasing when the radius is 16. Now, it looks like there's some information being omitted here, okay, but there hasn't. So the rates at which something has been increasing, if it says that and no variable is specified, you assume that that is with respect to time. Okay, if the rates at which something is increasing, you're usually talking about with respect to time, because rate is usually measured with respect to time. So for part B, what we're being asked to do here is to find ds by dt. Now, only do that, of course, if the second variable is not specified. Okay, just assume that. And that's when r is equal to 16 centimeters. All right. So how do we do this? So we go back to our summary. Can we construct ds by dt? Well, let's start by writing it down. ds by dt. Okay, so I know I need an s or ds in the numerator. So what candidates do I have? Well, it looks like I'm going to be using this one, ds by dr. And I think that's a good one to use. So I'm going to put that in. So that's going to be ds by dr. And we're also lucky because, or not lucky, but it's been set up that way. We also know what dr by dt is. So I can cancel out the drs. Okay. dr by dt is 1 over pi r squared. So let's plug those in. Hope that makes sense. So it's ds by dr, so that's going to be 8 pi r multiplied by dr by dt, which was 1 over pi r squared. So there's lots of cancelling going on here. Okay, so it looks like the pi's are going to cancel out. There and there. And r is going to cancel out there. So what we're left with? Something nice and simple. So we've got the 8 over, nothing else on top, 8 over r. So the rate of change of the surface area with respect to time is inversely proportional to the radius. Okay, so there we have it. Now we just have to plug in r equals 16 and we can see we're going to get a nice answer here. So therefore, when r equals 16 centimeters, ds by dr is going to equal 8 over the 16, which simply is going to equal 0.5. And the units, of course, are centimeters squared. Oh, I've just realized, I apologize. I've just written the wrong variable there. So that should be ds by dt. Sorry about that. ds by dt. I was going to say, because otherwise the units would cancel. So that's going to be ds by dt, which is 0.5 centimeters squared for the surface area per second. And that is the answer for B. Okay, no accuracy specified because it's an exact answer. All right, so just to summarize that we are actually using a summary of information here. So you're going to need to use the volume surface area formulas for things like this, create a summary, differentiate everything, and then try and piece together the derivative that you want using the information that you've got. Okay, and then you're going to be using the chain rule almost exclusively when you're doing this. Okay, so that's the first example done. All right, so worked example 2, we have a classic question. This is from an exam point of view as well. So it says the diagram shows a large cylindrical water tank, and there's some measurements given there. Now we have to read this information really carefully. Okay, not always will you get a diagram. The diameter of the circular cross-section of the tank is 10 meters. Okay, that's labeled. Water is flowing into the tank at a constant rate of 7.5 pi cubic meters per minute. Now, we have our first rate of change. Okay, I'm just going to highlight that. That's important. So can we write this down as a derivative? Well, this is water flowing in. So I'm just going to make sure this is really clear. So flowing in now we have 7.5 pi cubic meters per minute. So we can tell just using a bit of the dimensional analysis, like I said, we've got meters cubed there, which is a volume, and we've got minutes, which is time. So it's a dV by dt. So I'm going to write that down. Now, this is just flowing in. So I've not read the rest of the question, so just bear that in mind. dV by dt would be equal to 7.5 pi. Like so. So that's given in the second sentence. Now, at time t minutes, the height of the water in the tank is h meters. Right. You can see clearly from the diagram, because this is a cylindrical tank, that's not just because it's a nice shape. Okay, that means something. So we have to acknowledge that we've got a cylindrical shape here. So I can see that the volume of water, okay, so I'll write this down. The volume of water is going to be pi r squared. Just going to write that a bit more neatly. Pi r squared h, okay? Now, h is the variable. R, in this case, is fixed because it's a cylinder. And you can see from the diagram, because the length of the cross-section, or the diameter of the cross-section, I should say, is 10 meters, then we can now say that R is 5. So, therefore, given that R equals 5 meters, okay, we can now say that V is going to be pi multiplied by 5 squared. So just sub that in. Okay, multiplied by h. In other words, it's going to be 25 pi h. That's the volume. Again, I'm going to just draw attention to that. So that's a piece of information we've deduced from the text. Okay. Now, it says at time t minutes, the height of the water in the tank is h meters. Okay, yes, we've used that. Now, there is a tap at the point T at the bottom of the tank. Now, when the tap is open, water flows out of the tank at a rate of 0.45 pi h cubic meters per minute. Right, so this is really important, as everything is, as I keep saying. Now, flowing out, we have another rate of change. Now, flowing out, we just use that dimensional analysis again. So we've got cubic meters. Unfortunately, it's gone on to the second, or onto the next row, but it's the same units, isn't it? It's cubic meters per minute. So I can say that it's dV by dt again. Okay, and it's 0.45 pi h. Right, now, obviously they both can't be true. We've got two different situations here, water flowing in and water flowing out. So combined, so this means that the amount of water, or the rate the rate of change of V with respect to T is going to go like this. So it's going to be, the water flowing in is going to be the positive addition. So that's going to be positive. So it's going to be 7.5 pi. Okay, and I haven't left myself enough room. That's annoying. Subtract 0.45. In fact, I'm going to write that again. Let's give myself a bit more space here. I'll do it in a different color. So it's going to be like this. dV by dt is going to be 7.5 pi. Okay, so that's going to add to the amount of water, but then at the same time there's water flowing out, so that must be subtract 0.45 pi h. Okay, so that's putting it all together. dV by dt. Hope that makes sense, guys. Now, for the question, we're told to find the rate of change of the height of water. So it's a good idea to sort of write this mathematically in a second. So find the rate of change of the height of water t minutes after the tap has been opened. So mathematically, the height of the water there, that's obviously h. Okay, and then the time t minutes after the tap has been opened. So what we're being asked to do is find dH by dt, and then we don't need to find a specific time. It's just simply find dH by dt. Okay. So what do we know? Let's just build our summary. Okay, I've got bits of information all over the place here. So let's set up our summary and see what we can do. So the first thing, that all the information about the flow of water has given us dV by dt. That's really good news. So we know that's 7.5 pi, subtract 0.45 pi h as the water flowing in and the water flowing out. Okay, so we've got dV by dt. We also have V, the volume of the water. So it's just purely the water we're talking about here. So that's 25 pi h. That's the volume of water with respect to the height. And that was it. But what we can now do is we can say, okay, we can differentiate this V and get some more information. So I can now find out what dV by dH is. Okay, and it's 25 pi h, so it's just going to be 25 pi. Now, is that enough to get dH by dt? Let's try and construct dH by dt now. So dH by dt, well, I really need to desperately have a h on the top, dH on the top, in fact. Now, I can do that if I reciprocate the dH by dV, which I've, oh, sorry, I beg your pardon, the dV by dH, which I've got here. So if I reciprocate that, I can get the dH on top. So that's good. What else do I need? I need a dt on the bottom. So I need a dt on the bottom. Well, that means I can use this over here, which inevitably we were going to use because we've only got two derivatives from the whole question. So I'm going to plug that in. So that's going to be dV by dt. Okay, and because of the situation I'm in, this forces me to put a dV on the bottom, which is what I intended anyway. Okay, so that's how we get dH by dt. So we just put all this together now. So this is going to equal 1 over dV by dH, just reciprocating that, multiplied by dV by dt. Okay, so this is going to equal 1 over 25 pi. That's dH by dV, or 1 over dV dH. And then we multiply that by 7.5 pi subtract 0.45 pi h. Okay, now if you look at what we've got now, we can see there's some simplification that can be done here. We don't need to leave it like this. We've got pi in the denominator here. We've got pi here. So that means I can cancel the pi out. It's not dependent on pi whatsoever. So let's just get rid of that. Something else as well. There looks like some cancellation also in the 7.5, the 0.45, and the 25. But we'll deal with that in a moment. So if I just divide through by pi, and I'm going to expand it all. So we're going to get 7.5 over 25 for the first term, subtract 0.45 over 25, and that's obviously going to be h as well. So it's linear. And just continuing in this same vein, so if we do 7.5 over 25, you can just grab your calculator for this if you want to see how it simplifies. Okay. Oops, has it gone off? So we've got 7.5 over 25. So I'm suspecting that's going to simplify. Yeah, it's a 3 over 10. Okay, so I can put that in. Three over 10. And then the 0.45 over 25, go back to the calculator. Sorry for the overlay, it's just because there's not much room on the screen at this point. Over 25, so that's 0.45 over 25. Let's see what that simplifies to. 9 over 500. Okay, now the reason I'm doing this is sometimes you might be asked to write the answer in a particular way. So if there's any way you can simplify, then all the better. Now, obviously, you could factor out various things with this. I could take out the 3/10, for example, from this. So let's have a look at that. That's 0.3, in other words. So 1 minus 3 over 50 h. Okay, and then you could write that as decimals. It's completely up to you. Anyway, so that's basically it. So we read the question very carefully. You use the dimensions of the units to set up your derivatives. And now those are the specific derivatives in the context of the question, and they're usually numerical or have some specific variable in them, like h, like 0.45 pi h, like we got in this one. Use that, and then use the standard results for areas, volumes, etc., to create derivatives, and then write it all down in a summary, like we did right here with all these pieces of information. And then when you put them all together, you can create the derivative that it asks for in the question. Okay, so it's a bit of a puzzle, but the skills are things that you already have. It's the chain rule and basically manipulating algebra, essentially, which is what we always do. Okay, so that's the second worked example. Now we're just going to have a look at one more, and I would strongly advise you to have a go at as many of the questions as possible at the conclusion of this. All right, so in our final worked example, we're given very, very little information in terms of what the shape's actually going on. We haven't got any diagrams as such, but we're told it's an ice cube. Okay, we've got an ice cube of length x. loses its volume by evaporation at a rate proportional to its total surface area. And we have to show that the rate of decrease of the length of the ice cube is constant. Right, so let's draw our ice cube. So we'll assume it is actually a cube, which is, if you like drawing cubes, is a good opportunity. There we go, so there's my ice cube. Now, it's got a length of x millimeters. So because it's cubic, we know that all the dimensions are, of course, x. And we're given no other information. So let's see what we can deduce from this. What do we know? Well, total surface area, well, that's probably the harder one. Let's do the volume first. So we know that the volume is simply going to be x cubed. Okay, no problems there. Immediately, what I recommend we do is we differentiate that with respect to x. So dv by dx is simply going to be 3x squared. Okay, so that's the rate of change of the volume with respect to the length of its side. Okay, what else do we know? Well, we know about its total surface area. So if we just use the technique from lower school, from secondary school, GCSE, if we figure out the areas of the sides facing and then double it, and then we've got the total surface area. So looking at this, this is going to be x squared here. We've got x squared here and x squared here. So the total surface area which we will call S, is going to equal 2 lots of 3x squared, which is, of course, 6x squared. Okay, so I'm going to write that in my summary as well, and I'm going to differentiate that straight away. So we've got ds by dx. I don't know if we're going to use these, we'll just have to check. So ds by dx is, of course, going to be 2 times 6, which is 12x to the power 1. All right, and we'll just tell the examiner, the person marking it, what our variables are. So v is, of course, the volume. And S is the total surface area. All right. Right. Now, is there anything else we know? I don't think so. Let's see what the question actually is. Now we've just written down a lot of information and some derivatives. Show that the rate of decrease of the length of the ice cube is constant. Okay. Now, going back to the statement at the beginning, okay, like I said, we've written down a lot of information here, but what we're told in that first sentence is something absolutely key. We're told that an ice cube of length x loses volume by evaporation at a rate proportional to its surface area. Now that brings in the time variable. Okay, so it's the rate of evaporation. Evaporation is something that occurs over time. So volume, okay, and it's rate proportional. So it's with respect to time because the other variable isn't specified, essentially. Okay, so from the question, so all that stuff we've deduced is just from the facts about cubes, but from the question we know that dv by dt is proportional to its total surface area. All right, now we can obviously write that as dv by dt is equal to ks. Right, now we have something else for our summary. And what we have to figure out is the rate of decrease of the length of the ice cube. So find dx by dt. And notice it says decrease. So this is suggesting that this constant k is probably a negative constant. Okay. Right. So dx by dt. Let's construct it. Dx by dt. What do we need for this? Well, we need to have dx on top. What do we know about dx? Well, we've got dx by dv or dx by ds. Well, it kind of depends on the information they've given you. We're going to have to use this one because they've gone to so much trouble to tell us what it is. So I want to use dv by dt. And what's great about that is it's going to put the dt in the denominator. So I'm really pleased about that. So I'm going to put dv on top and dt on the bottom, and I've used it, which forces me to use dv over here. Okay, now that's just a reciprocal of dv by dx. So it looks like we're in business. So this is going to be 1 over dv by dx multiplied by dv by dt. Okay. So 1 over dv by dx. So this is going to be 1 over 3x squared. And just specify what I've used here. So I'm using this piece of information here, which we wrote down earlier on. Okay, that's what corresponds to here and here. Okay. All right, and then we multiply by dv by dt. Okay, so multiply that by dv by dt, which is ks. All right. Now, what can we do now? We have to show that it's constant. Now, s we can actually write in terms of x, which is really good. Because earlier, when we were just kind of going hell for leather, just writing down everything we knew about cubes, we discovered that s was 6x squared. So I can now swap the s for the 6x squared, which is really good. Or if you preferred, you could swap the 3x squared for a half s if you wanted to. It's completely up to you there. So this is going to be equal to 1 over 3x squared multiplied by k, but the k in turn is multiplied by 6x squared. And now we're going to see the cancellation take place. Okay, so we've got the x squared in the denominator. That's going to go with that. Okay, and the rest is just constant. So we're left with a rather elegant 6k over 3, which is, of course, just going to be 2k, which is a constant. And what I didn't state earlier was that k is a constant, which is what I should have done. And it's probably negative, but it doesn't matter. All you have to do is show that the rate of decrease of the length is constant, whether it's increasing or decreasing. In this situation, it's constant. Okay, so that concludes the worked examples. Please have a go at some of the questions. It's really important. And then when we move on to integration, you'll see how to solve these differential equations and apply your results to even more situations. Okay, so thank you. I hope you enjoyed the chapter. Okay, so that concludes the lesson and chapter 9.